I do need to make a small correction to your introduction. I'm not a neuroscientist, and I've never done anything with synapses, but I'm a cognitive scientist, as you will see. And after being the last speaker, I thought I should maybe say a few remarks about how my approach is quite different from everything that you've been hearing here. And so after lunch, I quickly made just a slide to briefly list some of the salient differences. I come from a background of admiration for the elegance and simplicity of mathematical and especially geometrical and theoretical physics types of things. And this might seem a totally wrong background to approach the mind, because it's a widespread view that in order to understand anything about the mind, you have to study the brain, and we've seen that over and over again here. But I have a different view. That is that in order to, even if you're interested in the brain, you need to first think about what are the problems that a behaving organism deals with in the world. And so I like to ask, well, what are the features of the mind or the principles of the mind that may have evolved as reflections or accommodations to features of the world. And because of the first point, I tend to look for very universal, very abstract sort of principles. And today, as examples, I'm going to really start with only two things about the world. These are such universal things, one doesn't anymore think about them than the fish thinks about water. They're just everywhere. And just one of these is that space is locally, at the biological scale, is three-dimensional and Euclidean. And it's populated with objects that belong to basic kinds, because it's in this kind of space, objects that have 6 degrees of freedom of rigid motion. So these are the things I start with, and I ask, well, what kind of a mind would be most effective in a world with just these very general abstract properties? And so I approach it this way rather than starting with, well, what do we find in the brain? And what I'm going to argue is that one can discover universal mental laws just from thinking about these very abstract features of the world, if you assume that the human being has evolved to be somehow, approach some kind of optimum functioning in this kind of world. Why did that advance? I guess it's timed out. So the third point was that the kind of applications of the things that I come up with are not going to pertain to everyday daily abilities such as understanding speech or ability to read, as in Brian's talk. But I do think they have some applications. I don't know how persuasive you'll find my arguments on this, but to some of the highest level cognitive achievements, such as discovering universal laws of physics. So we get kind of a closure of the loop from where I began and where I end up. So my talk's going to be organized into 4 groups, if I have time to get through them all. The first 3 have to do with 3 kinds of what I call universal cognitive principles. I should say right off that by universal I don't mean that earthworms have these. What I'm arguing is that any sufficiently intelligent sentient being, wherever they evolved in the universe, I would expect them to have approximated these principles. So So I'll move right on to the first one of these, which is has to do with generalization probability. Now, what I argue here is that learning is a very important thing. We've heard about it here. And I argue that there can be no comprehensive theory of learning without a theory of generalization, because we never confront exactly the same situation twice. So every response we make is, in a sense, a leap in the dark, and it must be based on some metric we have of similarity of this situation to previous situation or situations. Now, the study of generalization in psychology, my field, could be said to have begun with Pavlov, who found that if you rang a bell and fed the dog, then afterwards, if you rang the bell, the dog would salivate, and you could measure the amount of salivation. It's kind of sloppy data, but he did find that if you then rang a bell of a different pitch, you would still get salivation, but less so, and the more different in pitch, the less salivation. But you couldn't get any really precise data because the data were sloppy. And the question is, what is the dimension or measure of distance? And it turns out you can't just use a physical measure of difference in frequency, say, because there's things like octave generalization. It's not even monotonic. You need a psychological measure of difference. And this kind of consideration led me to develop the first method, a non-metric method of multidimensional scaling. This was actually the first application to empirical data I made of this this was published in '61. And with this method, you can take any matrix of similarity data, including generalization data, and you put it into the computer, and the computer uses a kind of a gradient descent method to find the closest approximation, moves points around in space corresponding to objects, in this case wavelengths of light, to find the closest approximation to a monotonic function, which is shown in the middle, and then you get out the spatial map, which looks like Newton's color circle. In fact, it's quite close to a circle. So this enables one then, and I'm not going to show any more of the multidimensional maps we get by this. And incidentally, it's called non-metric because it depends only on the rank order of the data. It's very good for psychology where we don't always know how to measure the similarity. All we need is the rank order, and you still get a metric. It's called a non-metric method because it uses non-metric data, but it gives you a metric solution, a very precise solution. It seems like you're getting something for nothing, but I can explain why that is sometime. So this then allows you to, what I'm going to focus on here is not the spatial maps, but the function that you get out. And it turned out they always have this kind of shape, and what I have fitted here is a simple exponential decay function. There's only one parameter being fit here, which has to do with the slope of the function. And these, and there's many more I've collected, and many more since then. The point is that that this function is determined by the data. It's not an artifact of the method. I can show that too. So this is the problem of generalization. So there's this idea you have this psychological space, or you have a psychological distance as the independent variable, so to speak, and then you can look at the probability that a response learned to one stimulus will be made to another, and you get these functions that look like exponentials. So then we want a theory of this, and here's the problem. So you have a stimulus, which is just a point in some representational space, and then there's some other stimulus that you test on later, and the problem the individual has is to decide whether the response should be made to this second stimulus, B. Well, it looks like there's not much basis for making a just judgment of probability. But my idea, and here's where I invoke this notion that the world is populated with objects that belong to sort of basic kinds, and the certain kind may have a certain kind of consequence, a certain kind of range of things may also be edible, just like A is. So here's the way I think about it. It's not a problem of it's not a failure of discrimination that leads to generalization. It's the cognitive act, because the organism in general very well knows that B is not the same as A. But the question is it enough similar that it could be of the same kind and have the same consequence? So the problem is there could be any, if that's all the information you have, there could be any number of sort of connected regions in this psychological space that belong to a certain kind. We don't want to make any particular assumption about the shape or size of these regions or their locations, but you can see that if you don't know which of these regions is the relevant one, it's certainly clear that the closer 2 points, like A and B, are together, the more likely they will fall in the same region and therefore be good candidates for being of that kind, therefore having the individual make that response. And so it's just a matter of integrating over all possible or plausible regions. And this was the basic equation I worked with. This first appeared in Science in 1987. Now, this was the basic equation for getting the generalization or the probability of responding. Because I've got a lot to cover, I'm not going to go into details, but there is a function, a weighting there that you have to assume some weighting on hypotheses based on the size of the region. And it turns out that makes hardly any difference. Any halfway reasonable function gives you essentially the same result. But if you use in particular the maximum entropy function, which is the minimum knowledge, and that's what we're starting with here is minimum knowledge, no knowledge really, then it turns out the integration gives exactly the exponential decay function. So that was what led me to the proposal of a universal law of generalization. Now, that doesn't deal with everything here because there's a question of what kind of metric does the space have. So you could even have exponential gradients, but if you're in more than one dimension, there's a question of whether they go off in the way shown on the left equally in all directions, or whether it depends on the direction. And these particular cases correspond to what in psychological parlance we refer to, well, as the Euclidean metric or a City-Bach metric. Mathematicians may speak of the L2 norm or L1 norm. There can be cases in between, as I'll show. Now, with regard to the theory, as I said, the shape of the size weighting function makes very little difference. But what about other things? How can we get these different metrics out? Because it turns out this is psychologically relevant. Different types of stimuli differ in the type of metric they require. Now you might think, well, of course, if the regions are, if these candidate consequential regions, I call them, were circular, then of course these functions would be circular as shown here. This is actual integration for that case. But what if they had a different shape? Well, it turns out that doesn't make much difference. If you assume the consequential regions are square, when you do the integration, it still gives you, at least if you're a ways away from the center, it gives you a virtually circular contour. So that can't be the way we get different metrics. And of course, if you have no knowledge about how the square is oriented, then they'll be exactly circular as in the preceding one. So how do you get a different metric? Well, if the size dimensions are uncorrelated along different axes of the space, then you get a very different situation. And this just shows for a rectangular kind of size distribution. now you see you don't get the circular ones, but you get something very close to the city block metric. And again, if you use the maximum entropy size functions, you get skipped over it. You get exactly the so-called city block metric. And if you vary the correlations assumed for the different the extensions of the consequential regions along different dimensions, orthogonal dimensions of space, you can vary anywhere between these. So you can get a whole family of metrics corresponding to the so-called Minkowski R metric, where R equals 1 for the city block metric and 2 for the Euclidean. This shows actually the distance metric, the non-Euclidean distance metric down, where R equals 1 gives you the city block and R equals 2 gives you the Euclidean metric, but you can have any other value greater than 1. And then you can do multidimensional scaling and with different values of R to see where you get the better fit using the stress measure of departure from monotonicity that my Bell Labs colleague Joe Krusko developed. And now on the left, you see for 3 different cases of stimuli that we say to have integral dimensions. And good examples would be colors, where there's no very salient dimension. It's hard to attend to the saturation of a color without also seeing its hue. I mean, they're just not separable things perceptually. So you would expect that the Euclidean metric might be best. And indeed, you can see for these 3 different cases, some for several sets of data, that you tend to get a lower value of stress, that is a better fit to the monotonic function for the value of R around 2. The bottom case isn't quite as clear, but at least it's lower than for 1. On the other hand, if you go to stimuli where the dimensions are separable, like squares varying in size and brightness, or things varying in size and orientation, where you can clearly sort of attend to one dimension versus the other, then you get just the opposite, where you get the lowest stress for the city block metric at R equals 1 and actually get the highest stress around the Euclidean value. So much for generalization probability. So now a related thing, that isn't right. There's I guess it is. So there's another general law, and that is what I refer to as discrimination time. It's a different time of task where you give a person 2 stimuli, and they get their reaction time for saying whether they're the same or different. And there too, I use the same theory essentially that I use for the generalization to deal with this, and made the assumption using the same model with the consequential regions with the weighting functions based on size and so on, and assumed that if you had 2 stimuli, of course, if you assumed that the consequential regions, the internal representation of the consequential regions were kind of firing off, if you will, with the speed of activation directly related to this initial weight, according to the size weighting function in the model, and then assume that the discrimination response occurred when you first got activation of a consequential region that included one stimulus but not the other, that would differentiate them. Then it turns out if you do the integration and all, you get, again, a concave upward descending function, but it's not an exponential function because, according to the theory, it goes to infinity as you approach 0 because it takes forever to, or nearly forever, to discriminate two things that are similar enough. And of course, the experimental data never go to infinity because the undergraduate student won't wait that long to see the difference. And so it always cuts off a little bit before that. But again, here's a number of sets of data. These, incidentally, are similar to the data we saw yesterday about, in fact, the lower right-hand corner is the case, again, of discriminating numbers of different sizes. And here there's no physical dimension. This just is, again, a point that there's an analog representation of digital numbers, but you see it's very close to that kind of predicted function. Now here's some more cases. Okay, moving right along to a different kind of thing, the least time transformation. And here, this refers to studies that my students and I studied on what we called mental rotation. So obviously the guy had to realize that they put the glass on the truck upside down and had to be rotated to fit in the window that they're repairing. Seems like I skipped one here. Oh, they're just in the wrong order. So this was the first study that I did with Jackie Metzler, appeared in Science in 1971, where we presented people with pairs of these objects. A lot of you may be familiar with this study, but asked them to operate a right-hand lever as soon as they determined that the two objects were the same shape, even though they're in different orientations, and left-hand lever as soon as they determined that they were inherently different in shape. And I used these sort of, as foils, these enantiomorphic objects, like in the bottom one, that cannot be rotated into congruence. And the top pair, of course, they differ by rotation in the picture plane, and the middle one, they differ by rotation in depth. And, oh, I forgot that I had these in the wrong order. Sorry. That's, you got to be careful which button you push when you're up here. In fact, I better go back to. It's annoying that it always, if you hit the wrong button, it resets you way back to the beginning. Okay. The data, as you see, are remarkably linear. The time it takes to detect that they're the same, despite difference in orientation, increases very linearly with the angular difference in the orientation all the way out to 180 degrees. And it's virtually the same function, whether it's a rotation in the picture plane or a rotation in depth. Even though you might think the picture plane one is a much simpler task because it's just the rigid rotation of the image on the retina, actually, whereas the other one is a very different thing as the object rotates. This just makes the point that the internal representation is not like the retinal image. It's a representation of the object in three-dimensional space. Now, it turns out that very same kind of phenomenon occurs in visual apparent motion, which we also heard about yesterday. So if we actually go back and forth between two of these images, you can get, I hope, the experience of this object rigidly moving in space. And many of our studies are able to show that the path in general is not a linear one, but is a curved path. And not only that, but we get very similar sorts of functions where the minimum onset time in the two alternating things for which the person experiences a rigid motion increases linearly with the angular difference in orientation already out to 180 degrees. And again, it makes no difference in terms of the slopes of this function as to whether it's a rotation picture plane or in depth. This and great amount of further work we did was summarized in the book that I authored with Lynn Cooper, which included both mental transformations of various sorts and apparent motion phenomena. So now what about the theory? Well, here, if you consider an object in space, like one of these, it has 6 degrees of freedom of motion, 3 of translation, 3 of rotation, and you can represent this in terms of the so-called proper Euclidean group, which is a semi-direct product of the translation group and the rotation group. The translation group is very intuitive, and it just has to do with linear motions in space, and but the rotation group is a more exotic object. You can show a plane through that three-dimensional space of possible rotations. Look like this, where I use an object labeled with T, F, and R for top, front, right, and so on. But that's just one two-dimensional section through it, and even that, this is flattened, as I say. In terms of the actual intrinsic metric of this space, it's like a hemisphere, which is sort of an inelegant thing, and the mathematicians or theoretical physicists would complete the sphere. You have a double covering thing, and that actually is kind of interesting because in theoretical physics, the fermion, according to quantum mechanics, unlike objects we're familiar with, is not returned to its initial state by a 360-degree rotation, but you have to make 2 complete rotations, which corresponds to going around this covering. So it has not only mathematical elegance, but a physical reality that corresponds to it, as well as a psychological reality. Now, this gets more complicated when you consider objects that have various degrees of symmetry, as here, central symmetry. So with another student, Joyce Farrell, who happens to be the wife of Brian Wandel, who you just heard speak, and when she was a graduate student with me, we did studies with objects where we varied the degree of symmetry, like you see this polygon at the top, which is pretty much asymmetric, and then you can gradually make it more symmetric till it's completely centrally symmetric. And of course, with this centrally symmetric one, it rotates into itself through 180 degrees. So the psychological representation, according to all this, would be for a truly completely asymmetric object, you would have one big circle corresponding to 180-degree rotation. At the bottom, if it was completely symmetric, since it maps into itself, 360-degree up top, and with a centrally symmetric one, it maps into itself with 180 degrees, so that big circle at the top has to distort and fold onto itself to make a double wound circle, as shown at the bottom. And in between, it goes through something that can only be properly represented in a 4-dimensional space. It corresponds to a spiral around a torus, and it's shown there. And if you connect corresponding points that are going to map into themselves for the complete symmetry, that sweeps out a Mobius strip in this 4-dimensional space. Rather exotic object, and you might say, well, Shepard's getting pretty far away from the mind and cognition. There can't be anything like that in the human brain. But in fact, when we applied multidimensional scaling to actual chronometric data collected from subjects, we got a 4-dimensional solution in which 2 dimensions, the one shown by the plot at the top left, gave the single wound circle, and the other one on the right was the double wound circle, and when in the four-dimensional space, these are exactly that intermediate curve that exists in four-dimensional space, and you can show the for objects of different degrees of symmetry, you got different weightings of the single wound or the double wound circle, and that's shown at the bottom for 25%, 50%, 75% symmetry, so that you get virtually no weight on the double wound circle. Virtually no weight of the asymmetric object on the double wound circle, and highest weight for the symmetrical objects on the double wound circle. I hope I said that right. I hope. At any rate, the idea there is that this is actually optimum in our kind of world. Just as I claim that this probability law of generalization is optimum in the minimum knowledge situation of generalization in our kind of world where there are objects that belong to kinds. Likewise, I'm saying in the case of this least time principle, it's very important to establish as quickly as possible whether two objects are the same or not. And to do that, I claim there's an analog process of a motion over the simplest, most direct path according to kinematic geometry, and those are just the paths that occur in this convoluted space I was talking about. So now move on to symmetry. Now, we are very attuned to symmetry. Symmetries appeal to us. You see it in the patterns of all cultures, and we immediately pick up on symmetries. And of course, symmetry is just invariance under transformation. And what I've been talking about is this power that we have in the mind of transformation. And by the way, when am I guess I still have a little more time. So here there's some different kinds of symmetries of reflection, translation, rotation, and more generally screw displacement, which I haven't talked about much there, shown the lower right. I'm going to now talk about applications of all this to creative thought. And of course, as we all know, Einstein said he did not reach his discoveries through articulated thought or language, but imagining the effects of transformations and so on. And I'm going to suggest that a lot of the great discoveries in the history of physics, and I can't go very far with that today, may have been or could have been achieved through thought experiments using this mental capability of mental transformation and appreciating invariance under transformation. And so very abstract principles such as symmetry are, I think, fundamental here. Now, what this leads to is a very outrageous proposal that there may not be that much difference between establishing rules or laws or principles in mathematics and in physics, even though the former is thought to be compatible with a sort of rationalistic approach, whereas the latter certainly requires empirical study of the world. But let's look at a couple of cases. Let's take a case from mathematics first. The Pythagorean theorem, and there have been many proofs of that. But I think this is the one that's attributed to Pythagoras himself, in which one can imagine this triangle duplicated into making 3 copies of the original triangle and arranging them in a square like that, and then sliding the 2 on the left down, tipping triangle 1 up, and rotating triangle 2 up, and then what you get is the thing on the right there compared with the original arrangement. And you can see that the shaded square, the shaded figure on the right, all the sides are the length of the hypotenuse. Since they're all the same length, and from the symmetry of it, you can see that it's got to be invariant under rotation, and therefore it's a square, not some other quadrilateral. And now you see that in both cases, the 4 light triangles fill a portion of the square, but in different ways. And the areas left, the shaded areas, must be identical in area on the left and right. And on the left, it's a squared plus b squared, and on the right, it's c squared. QED. So that's a mathematical proof, or proof of a mathematical theorem, if you will. And it's not perhaps surprising that you can do it just by thought. You don't have to go make measurements in the world. But now let's look at Archimedes' law of the lever. And here I do a thought experiment. And possibly Archimedes did this. So I'm arguing he didn't have to put any weights on any beam balance. He could see that in his mind's eye, if he had 4 identical weights, and by symmetry, of course, it's invariant under permutations of those weights. But at any rate, it's clear that if you put 2 on each side of the fulcrum, equally distant out, it's got to balance. There's no reason for one side to go down more than the other. Well, you can extend this further, and you can modify the beam balance by cutting off a center part on the right and putting a secondary fulcrum through there. And now, if you redistribute the weights, 2 1 unit out on the left and 2 1 unit out on the right, on the secondary beam, and that combined weight gets communicated to the main beam through the secondary fulcrum. It's identical to the first situation, so it's still got a balance. And furthermore, no matter how far you move those 2 weights on the secondary beam out or together, it's still got a balance. And you can see from that all of these satisfy the Archimedean rule. And you can do it much more generally. I won't take time to go through it with any distribution of weights. By if it's balances, then you can always take any 2 weights the same distance out and move them together to their midpoint. And by just doing that by process, I won't go through all the steps, you end up eventually, if it balanced in the first place, they're going to all end up above the fulcrum. And so it's a general proof of the Archimedes law of the lever. Very interesting thing occurred to me after I worked out that example, that the 2 things are connected. That the thought experiment here, you find yourself in a long, narrow room, and there are 3 long, rigid rods of the same diameter material, and you're asked to say, will these 3 rods make a right triangle when they're put together? And you can't, it isn't wide enough to actually lay them out to check it, but there does have to be a long beam balance in there, and it turns out that if you lay the 2 shorter ones on the left, like that, and the longer one on the right, and it balances. If and only if it balances, you know it'll make a right triangle if you were to assemble them. So it's a curious connection. We'll quickly go through just a few very simple examples of other thought experiments. Probably the most discussed one that has to do with Galileo's law of falling bodies. Now, this is not exactly Galileo's thought experiment, which was very elegant itself, but I modified it slightly. Or in fact, this is the way I thought of it before I knew exactly what Galileo had proposed. But so I imagine Galileo imagining himself at the top of the Leaning Tower with 3 identical bricks. And since they're identical, any result with them should be invariant under the transformation, permutation of the bricks. In particular, if you drop the 3 bricks, there's no reason for one of them to reach the ground before any other. And then you'd think, well, wait a minute, if I put a little crazy glue between 2 of these bricks, it's now one big brick. And whereas Aristotle reportedly thought they should drop twice as fast, this bigger object, than the smaller, it's clear that it makes no sense to say that this little dab of glue will now cause the 2 bricks to fall faster. So we reached the conclusion that the rate of fall, ignoring air resistance, is independent of weight. Another one is of Newton's 3 laws of motion, the equal and opposite, the action equal opposite reaction is the most uniquely Newton's. The other 2 can be traced back to others. But so I imagine Sir Isaac out on a lake with 2 boats filled with apples. Well, he has his boat filled with apples. There's another one, and he thinks, well, if I try to push the other boat away from mine, I can see that from symmetry, you can't push one boat away without the other one going equally away. So that's a very simple example of symmetry leading to physical law. And I'm just going to talk about Einstein. Well, we're talking about falling bodies and so on. And general relativity. If Einstein imagines himself in an elevator that's supporting cable severed and they're free falling, he feels no force. That is, unlike standing on a solid platform where you feel that the floor is pressing up against your feet and supporting you, there's no force in the falling elevator, so he's sort of floating up there. And since there's no force operating, if a beam of light goes through the elevator, there's no reason for it to bend up or down. It's going to go straight through. It's not going to curve. However, from an external observer's point of view, the elevator is accelerating past due to the so-called force of gravity. And therefore, a beam of light that goes straight from the observer in the elevator must curve, approximately parabolic from the external observer, and the external observer feels the force of gravity, and that the external observer is being supported, feels the pressure on his feet, and therefore attributes the bending of the light to the gravity. But of course, for Einstein, unlike Newton, there is no force of gravity, because here's the Newtonian picture where I'm just reducing it to 2 dimensions, space horizontally, time vertically, and so you have a very massive object, a large star or black hole or something. It is just moving upwards in time, so to speak, and a small planetoid is attracted, according to Newtonian view, by the inverse square law of attraction, and it curves in this parabolic way until, let's suppose, it collides, impacts with the... So that's a theory based on force. Now, if you start thinking about space can be curved, and then you can curve it that way, and then you can curve it that way, and you got a negatively curved space-time, and now there's no force operating. The planetoid is just following what would be it's a geodesic, this closest thing to a straight line on this curved surface. It's just what you get if you laid a tape out. And so you explain the same physical phenomenon, but without a force, but by taking account of this distortion of space-time by the gravitating body. Well, I'm going to wind up here. Here's sort of, in terms of this kind of thinking, and I didn't have nearly enough time to even begin to talk about how these sorts of thought experiments could operate for other theories, including quantum mechanics, but we do know that symmetry is fundamental in all of these theories. And again, going against the prevailing empiricist view, it's striking that once you get these theories, and the higher up you get in this kind of thing, the more structured the theories become and the harder it is to make any small adjustments. The less arbitrary they seem. And a number of physicists have pointed this out. It's very difficult to make small changes in general relativity or quantum mechanics without disrupting the whole thing. And sometimes it leads people to say, gee, I don't think it could have been otherwise. And yet we know that general relativity and quantum mechanics are inconsistent with each other. And the point is, whatever theory is eventually developed that subsumes those as special cases consistently, that event will be as major an advance as either coming up with general relativity or quantum mechanics without collecting another single datum. Just think about that. So quantum mechanics and relativity are somehow don't yet fit together quite. And, you know, I had more I could go on to, but I think my time's up, and I better leave a moment for any questions or, yeah.
So we'll entertain questions for Professor Shepard. There's a question back here. Could we have the microphone, please? Wait for the microphone, please. Identify yourself. We have to keep the needs of our video audience in mind.
Okay. I'm Ariella Popple from here. And so I've always thought about Pythagoras that way. And I always thought that mathematicians have some different way of thinking about it, and that's why I'm not a mathematician. So I would just be really curious to hear, you know, like by show of hands from the audience, who has never thought about Pythagoras that way. Thank you. And response, or, yeah.
I'm sorry, who is what? What are people raising?
Well,
who has not thought of Pythagorean theorem in terms of that rearrangement of the square?
Okay. There's somebody over there.
Okay, next question, please.
There's somebody over there.
Yes, over here?
No, I haven't.
Oh, okay. All right. Another question?
Well, either...
Well, we have one down here.
Okay, I was worried. It seemed like either what I said was totally obvious or totally wrong. I wasn't sure.
Thank you for a beautiful talk. So, you know, you started saying, you know, mind and, you know, brain, and, you know, so you're just going to study the principles of the mind as it is. But as you sort of reflect back, I mean, symmetry is one thing you brought out, and the generalization, you know, the psychological generalization. What are the primitives of the mind in, you know, in your mind?
Well, there's probably many of them. I've just sort of focused on these two kinds of things, one having to do with space, very, very abstract general principles, and claimed that just assuming if we're somehow optimized for functioning in a three-dimensional Euclidean world, we can get all kinds of things out of that that seem very actually far from our everyday experience. When you really go into the geometry of the spaces that are implied and the paths in these spaces and so on. And likewise, the other case was the idea that the world is filled with objects that belong to some kind of basic kinds, and you can make, just from that fact, you can get a mental law. Now, obviously there's a lot more to mind than just exponential generalization and least path transformation, but I just gave these two examples, and I would like to know more about other things. But I'm attracted to things that are possible universals and have a certain elegance to them, and I tend to shy away from things that look like they have a lot of complexity that I don't understand. So,
one question that I had, it seemed to me, I recall when your book came out on the geometrical transformations of objects and the ability of people to decide whether they were the same or not. And it seemed to me that that was also a statement about the closeness or distance measure between thought processes, because that's really what's going on there, right? You're sort of judging, well, is one thought process more difficult than another? Is that a view that you subscribe to?
I wouldn't quite put it that way. But one thing that's shared between what I'm saying here and a number of things that other people have said here is that the spirit of what I'm doing is, first of all, it's connected with the perceptual system more than with language, and therefore it invokes kind of analog-like processes rather than sort of more digital processes. And I believe that these are very fundamental for creative thinking, and of course language is important too. There's no doubt about that. Well,
good. And one last question over here, please. Wait for the microphone, please.
Hi, Stan Klein from Berkeley. I really appreciated the elegance and the beauty of it, but I am curious about bringing it to the place that you didn't want to go, which is neuroscience and what's going on in the brain. So, like, for example, in the mental rotations, what has happened in the last years? For example, I remember, I don't know if it was Lynn Cooper, looking at saccades or counting what the processing is. And like, has anybody done fMRI? Like, where is it being done, and anything like that?
I'm ashamed to say I don't know. I left Stanford and moved off to a retirement community. And a little bit isolated. I don't keep up with the literature. I know that there are people doing things with that, and I've actually gone off into extending this approach that I talk about with the cognitive grounds of science here to the cognitive grounds of ethics and the problem of free will and reconciling it with determinism. So I've been really keep talking more to philosophers, and I really maybe someone else here knows whether there's more work relating the kind of empirical stuff we had on behavior to what might be reasonable models in the brain. I mean, I knew of some of the things that were being done 10 years ago, but I don't know the present status.
Well, thank you again, Professor Shepard.